I'm Kat. I lead Dynatrace's privacy engineering team and also collaborate on privacy research with our research division.
And I'm Patrick, working at Dynatrace while I'm finishing my degree at TU Graz, focusing on information security.
Before we dive into our research today on reconstruction attacks, I'd like to set the stage. Dynatrace is an observability platform, so we conducted our attacks against observability data. But what is that? Some of you might have worked with observability tooling. If you haven't, the goal is to provide insights into what your software is doing, traditionally via the 3 pillars of logs, metrics, and traces. These really become essential when you have a large distributed system. If you have 10,000 servers or 100,000 servers, there's no way you can individually check the logs and performance on each one. You need to gather all of this data together in one place and automatically derive some insights from it. Beyond logs and metrics, you may also want traces to understand the interactions between systems during each request, so that when there's an error or a performance issue, you can easily find out which system is the culprit. And to trace this full request flow, we need to link the things that are happening in the front end, in the UI, with the things that are happening in the back end. And that's where client-side instrumentation in the user's browser comes in. Real user monitoring, or RUM, which is the data type that we're particularly interested in today, builds on top of that to gather data about the user's experience and their interactions with the application. And this level of detail is useful for troubleshooting and business decision making. For example, we might want to understand the level of adoption of a new product feature. But of course, there are potential privacy concerns here as well. If you mistakenly use RUM to collect all user inputs that are typed into forms, then you're going to be gathering all kinds of personal and sensitive data. Even API design can have an impact. If you pass sensitive data in query parameters, for example, then it's going to get collected either by your observability tooling or the observability tooling of someone else further up the request chain. This means that 2 things are essential. Firstly, observability tooling needs to have privacy features built in, like sensitive data detection and redaction. And the developers also need to understand how to avoid these potential privacy pitfalls when they're instrumenting their applications. So that's the context for why we have a privacy engineering team at Dynatrace and why this RUM data might be interesting from an offensive privacy perspective.
So that's observability, but what are reconstruction attacks and what's our attack scenario? In the context of a reconstruction attack, we have an attacker that wants to retrieve information from a secret database, which he does not have access to. Instead, the attacker has access to statistics that are derived from the secret database. And each of those statistics is essentially just a linear function, and linear functions are not irreversible. An attacker can use these statistics as constraints of a linear program, which he can then solve in order to get a reconstruction of the dataset. Hence the naming, you use a linear program to reconstruct the database, so this is a linear reconstruction attack. These linear programs can be solved for an exact solution given enough constraints, or in the context of reconstruction attacks, enough statistics. The problem with this approach is that the linear programs can be quite large for realistic datasets, which means that this may be computationally infeasible. So let's have a look at a different type of reconstruction, namely the confidence rank reconstruction. This one works in an inherently different way because it actually uses synthetic data generation, which is actually a privacy-enhancing technology. With synthetic data generation, you generate a second database, which has similar statistics, but the rows themselves are not collected from users directly. They're just generated in order to mimic the statistics. So this enhances the privacy. But in practice, there will still be some rows that match some rows from the secret database. And in practice, these will be more common than entirely random rows, which means that an attacker can abuse this fact by just generating multiple synthetic datasets and then checking the number of occurrences of each unique row. If you sort the rows by their number of occurrences, then you have something that we call the confidence set, which is an ordered set, which means that if a row has more occurrences, the attacker has a higher confidence that this is an actual row matching a row from the secret database. So all in all, this is a very empirical reconstruction attack to reconstruct a portion of the original data set in contrast to the exact reconstruction we saw in the linear reconstruction attack. Finally, let's have a look at some common reconstruction attack settings. Most commonly studied would be that of the publication of a data set, like census data, where making the data set publicly available is in the public interest, but we still want to protect individual privacy. Then we have the malicious provider scenario, where the provider is maliciously collecting user data or training a model, and users want to protect themselves against that. Much less commonly studied would be the malicious user scenario we have in the case of RUM. We assume that we, the provider, are trusted, and our customer, who is using Dynatrace RUM, is also trustworthy, but they have a malicious insider and malicious employee who abuses their access to RUM statistics.
Thanks, Patrick. So let's dig into this malicious user scenario a bit further. First off, why are we thinking about it? Well, we're a business-to-business provider. We want to protect privacy, but we don't decide how RUM gets used and what data is collected with it. Our customers decide that. And customer confidentiality is essential. We've got customers in highly regulated sectors, such as government and healthcare. So we can't be looking over their shoulders to audit their use cases and tell them how to protect privacy in their specific use case. Instead, we just try to support them in figuring that out for themselves. And one of the ways we do that is by establishing privacy-paved roads, so that the easiest way to configure and use the product is also the privacy-preserving way. And that, of course, includes offering privacy features. And when we're trying to decide which ones to invest in, privacy threat modeling and offensive privacy research can help us understand which would be our best investments. We've been thinking about this malicious user scenario specifically for RUM, and we have an idea for a product feature that could help. Instead of offering all or nothing access to RUM data per monitored application for our customers' users of Dynatrace, we want to add a new statistics-only API, which could be useful for customer employees who are more interested in broader trends and don't have a good reason to access the raw data. And for context, some of our customers have thousands of Dynatrace users. So this is really, really important. If you only have 10 users, perhaps you can justify granting raw access to the data, but when we're talking about thousands, we need more fine-grained access control. So we think this is a good idea, and we've been trying to make the business case for this feature, but the implementation effort is going to be quite high. So we need to prove that it will actually provide meaningful privacy guarantees. And in particular, we're wary of the potential for reconstruction attacks. We know that we could try to mitigate that by applying differential privacy, but it's going to take a lot of trial and error to find the right parameters so that these noisy statistics will still be useful for all of our customers. So we want to give it a try without adding noise. We're going to threat model this, conduct some reconstruction attacks against a prototype, and hopefully use those results directly in our business case as evidence. So let's threat model. There are some great privacy threat modeling frameworks out there, such as this one, Easdon. But I find applying them in this business-to-business context where we don't know our customers' use cases and exactly what data they're collecting is really hard. It adds another level of abstraction. Easdon focuses on these 7 categories of privacy threat, and depending on the use case for RUM, every single one of them might be a threat to monitored users, or none at all. So we get a bit stuck here. We need to take a more tactical, context-specific perspective. In security, there's this concept of the unified attack kill chain. When we're trying to get inside our attacker's head, we're thinking about how will they get into the network, how will they move through the network to compromise further systems, and then how will they get out again to achieve their attack objectives. And those attack objectives really matter because they're going to influence their behavior at every stage of the attack. And we can define a similar 3-stage kill chain for reconstruction attacks. Instead of those stages of in, through, and out, we have first data collection, gathering lots of statistics, then data reconstruction to recover the underlying data set from those statistics, and finally exploiting the recovered data to try to achieve the attacker's objectives. And our actors in this scenario are developers who actually have a good reason to have raw access to the data. They need that for troubleshooting. Then business analysts, who are our target audience for this statistics-only feature, and our insider threat. And we can make an informed assumption here that our insider threat is not a developer, because if they are a developer of this application, then they almost certainly have an easier way to achieve their attack objectives than conducting a reconstruction attack. Maybe they have direct access to the user's database, for example. So here, this helps us narrow our scope to thinking about the objectives of a malicious business analyst. And to determine those objectives, we look at the different sectors that our customers are based in, and for each sector, think through what kind of data might be collected about users in that sector, and how might a malicious business analyst exploit that data. You can imagine the potential for exploitation here is quite different if we're talking about a bank versus a telecommunications company, electricity provider, or an airline. Now, digging into these per sector personas could be an entire talk in itself. I sadly don't have time to look at them in detail today. But I really want to stress how important they are as a complement to this privacy kill chain approach to enable us to actually come to some concrete conclusions when we're doing privacy threat modeling at this very high abstraction level in the business-to-business setting.
All right, enough background. Let's get some practice in. Let's start with our attacker setup. In our scenario, our attacker has a relatively low budget, performing the reconstruction attacks on his work laptop with the specs listed here. We also tried running the attack on more powerful cloud infrastructure, but due to convenience and also time constraints, we mostly stuck to this local setup. The code for the synthetic dataset generation uses code adapted from Amazon Research. The main adaptation from that is the removal of noise, so we're only dealing with these noiseless statistics. For the database model, we selected these 9 columns from the Dynatrace user session API. And finally, where did we get our actual data from? We generated that using the open source Easy Travel demo application, which is a demo application which generates load on a fictional travel agency website. So the generated users are from a global pool and thus quite diverse. So we have a very high dimensionality in our database. For the linear reconstruction attack, we use the lpsolve library using R. And one key result already, it was impossible to run the linear reconstruction on the full data set. So instead, we first tried to run it on very small data sets and increase the size gradually in order to find a point where the attack does not work anymore. For very small data sets, the reconstruction worked well. In the table, you can see the time it took for a full reconstruction. So every single row is reconstructed perfectly in all of our experiments there. For larger sizes, we ran into these computational constraints, so it didn't work out anymore. Because we assumed the sparsity to be constant, we got an exponential runtime with the database size, since both the number of the linear constraints and also the sizes of the constraints increased. So this attack became infeasible. So let's have a look at the second attack, the confidence rank reconstruction. For the results, we cannot make a direct comparison because the setting and the result is inherently different. We cannot just measure the time it takes for the reconstruction to be complete because the time is a constraint that we set when we run the reconstruction. So we just let the attack run for 72 hours. So our attacker runs the reconstruction over the weekend, and then we did some empirical evaluations on the output. The first one is called the match rate. This is a function over the confidence set, and it states for the top n rows the proportion of correct matches that the matches some row in the secret database. And for that, the expectation is that it's continuously decreasing, which captures the fact that correct matches should have higher confidence. The second metric we analyzed is the cumulative match rate, and this is essentially just the integral of the previous graph for each iteration. And this is trying to capture the fact that letting the reconstruction run for longer gives the attacker better results, because a higher cumulative match rate means both more matches and matches with higher confidence. So what are some takeaways from that? Running the attack for a relatively long time enables the attacker to reconstruct a very small portion of the secret database. So that's less than 2% with high confidence. So targeting an individual is very difficult. Another challenge a real attack would have is that the database wouldn't be fixed. The effects of a rolling database is something we have not analyzed in these experiments, but would certainly be another big factor in an actual attacker scenario.
All right, so with those results, we've ruled out some attacker objectives, but how can we mitigate partial recovery of the dataset? Let's revisit our privacy kill chain to see what we could do. As we knew from the very start, we could apply differential privacy at the data reconstruction stage. But actually, we have other options here, and I think that's the real advantage of this kill chain approach. It gets us thinking about what the attacker needs to do at each stage. The very first thing they've got to do is collect lots of statistics. And we could actually detect them there with API rate limiting and automatic detection of anomalous query behavior. Actually, in our product context, that would be much easier to implement than differential privacy because anomaly detection is already a core product feature. So that would be the mitigation that we decided on for this business case. But in a different context, for a different product, you might instead focus on reducing the exploitation or the exploitability of that data by, for example, segregating access to the data, deciding not to collect some data altogether because it's just too risky, or applying layers of pseudonymization, with the overall goal being that no one insider ever gets the full statistical picture with when these statistics are highly exploitable. And why am I so confident that we can mitigate data collection? Well, Patrick mentioned that the confidence rank reconstruction attack only managed to recover 2% of the dataset. That took 1 million API queries to get enough statistics. So with the default API rate limiting, that's going to take 2 weeks of the attacker hammering us with requests to try and gather all that data. That's very noisy, very easy to detect, and we can alert the customer about it. The added bonus here is that we don't need to make any assumptions about the attacker's computational resources if we're mitigating at this stage. And this is a bottleneck for them where parallelizing the attack won't help them because with the same login, they're always subject to the same rate limiting. Whereas parallelizing that data reconstruction stage would help them. But before they can get there, they've got to get these statistics. So to wrap up, we conducted an offensive privacy analysis of this proposed product feature and found that it would provide meaningful privacy guarantees without using differential privacy for the statistics. So now we can discuss this again, having significantly strengthened the business case. And I would love to hear if any of you have tried a similar approach. I don't hear much about it in public. I don't know whether we're all using offensive privacy analysis and just not talking about it. So maybe let's have a talk about it at the conference today. Another thing to consider is that in addition to using this to convince internal stakeholders, you can also publish this offensive privacy analysis where that's appropriate, so the customers have evidence of your privacy claims. All right, thank you for listening.